Right, should be continuing with this series of videos. Just responding to the conventional theory of physics as presented in university and such. Professor Lewin in this case. And I will just point out parts that I think need more detail, need something to be said. So that's what I'll do.
Here are the topics, the way I see them.
Alright, that
on
did
the web.
work.
Look on the lecture supplements of today. And you can...
Alright, that did work. Alright, so this is the exam review. So sometimes there's something in these review videos where he does an experiment or something. So I didn't play the last one, so I'll play this one just so we don't miss something that might be interesting or important.
Download them. I want to point out that the discount is very reasonable because these magnets are broken. And when you break a magnet, you end up with two monopoles, so you get 50% off. You should know better by looking at the key equation there.
Alright, so they're not all of them are key equations apparently. But again, the idea that monopoles aren't going to change, recognizing the existence of monopoles isn't going to change anything in the sense that we already know what charge does, and so it's just recognizing that charge is fundamentally a monopole phenomenon. So, but the fact that they haven't recognized that there is no magnetism without the function of protons and electrons, it just sort of startles me.
That magnetic monopoles don't exist, but that's a detail. I want you to appreciate that I cannot possibly cover today these topics in any depth, nor can I cover all of these during a 50-minute exam. So please understand that this review is highly incomplete, and what is not covered today can and will be on the exam. I'm interested in concepts, I'm not interested in math.
So this is the bizarre part, right? Because most of it's math, and concepts are just kind of fluffed over. You know, they're, again, the engineered experiments to prove a point, but if you fiddle with the experiment, maybe you can prove some other points. And so concepts, in my opinion, are non-existent in the sense that they have no, you can't have a concept without axioms or precepts, and they don't have any underlying theory for function. They just claim the existence of a thing that's associated with another thing, that's associated with another thing, and they're defining effects, but they really don't have any definition of causes except stuff they make up. And I'm just saying, yes, they're nice placeholders, but it's getting the right answer for the wrong reason.
There will be 7 problems. 5 of the 7 problems have only one question. And 2 problems have 2 questions. I don't think that the length of the exam is going to be an issue. This exam is taken by several instructors, took them 15 to 18 minutes, and that's normally my objective. Courtesy of Professor Belcher, we have tests on the website. I don't have the solutions. There's only so much I can do. I'm very grateful.
Kind of bizarre. I mean, if they had, it'd be nice to have sample questions where you actually see how the right way to do it is, and so you can see, check to see if you try it first, and then you can look at the answer and say, oh, gee, yeah, I see what I missed. There's no answers. It's just like, thanks, but no thanks.
To Professor Belcher that he made these exams available. If you can't do some of the problems, I would suggest you see your tutors or you see your instructor. I will also be available all day afternoon. Not tomorrow, because tomorrow afternoon I'll be in 26100 all afternoon to work on demonstrations for the next week. Many of these problems are straightforward. You may also want to consult your study guide. All right, let's first start with Biot-Savart. There are not too many problems that one can do with Biot-Savart. dB equals mu 0 divided by 4 pi times the current, the L cross R divided by...
All right. So, just be nice to know, why is the mu zero in there? Why is the permutivity of space relevant? 4 pi, why is it in there? What's it do? It's a real number. 4, it's like 12 whatever, 0.5 or something. Why is it important? 12.5 divided into the permeability of space. I mean, it's, and then dB, I don't even know what that is. That's a vector, so, I don't know. Yeah. We know that d is an important thing, distance, and t is an important thing, time. So dl, I don't know what that is, distance and length. I don't know, but whatever.
R squared. That's the formalism. A classic problem that you probably have done. We have point P here at a distance d from a wire, and the current through the wire is I. If you want to know what the magnetic field at P is, you can use BO sub I. It would be a stupid thing to do, but you can do it. You take then a small element dl here of the wire. This distance is r. This is the unit vector r that you have in this equation. And you can calculate then what the contribution to the magnetic field right here is. It comes out of the blackboard due to this section dl.
So all you're doing is recognizing how far away you are from all these sections. So you have to do the integral. So I don't see how you can do it from a distance. Well, I guess you're comparing the distances, the two different distances, this distance plus the hypotenuse difference, and the hypotenuse distance is the extra distance, and that tells you how big d is on the other side. So I guess that's how it's relevant.
This angle is theta, and the sine of theta is d divided by r. And then you have to do an integral over the whole wire, theta 0 to pi. And then you get the magnetic field here. Not a very smart thing to do, a waste of time. Because clearly the way to do this is to use Ampere's law, which is the one at the bottom there.
Yeah, just take the distance, and that'll tell you everything you need to know in the current. You don't need to know anything else. How far away are you? Period.
In which case you would construct a closed loop with radius d. This loop is perpendicular to the blackboard. Try to make you see it three-dimensionally. You have to attach an open surface to that closed loop. Any open surface will do. Let's make the open surface flat. And then we apply Ampere's law, which is the one at the bottom there. We don't have the second portion because there is no changing electric flux. We don't deal with kappa m at all, so we simply have that B times 2 pi d that is going around in this circle, because I know that B is tangentially to that circle. I also even know the direction according to the right-hand corkscrew rule coming out of the blackboard here. So as I go around the circle, B and the dl that you see there at the bottom are in the same direction. So I get 2 pi b times d equals mu 0 times the current that penetrates that surface, and that is I. And so the answer is very simple, mu 0 I divided by 2 pi d. That's the way you would do this problem, and you would stay away from BO sub I. There is one particular problem.
You could get rid of the mu 0 and the 2 pi probably, because they're probably related numbers, but whatever.
Whereby Ampere's law will fail. Of course, Ampere's law in general works when we have cylindrical symmetry. This is cylindrical symmetry. There's one problem where Ampere's law bitterly fails and where BO sub I is highly superior. I have here a conducting loop. It's a circle, and you're being asked, it runs a certain current I, and you're being asked what is the magnetic field right at the center. It only works for the center. You could not find what the magnetic field is here. We did that in class. You probably also did that for your homework. BO sub I will immediately give you the answer, and I will leave you with that. And Ampere's law won't work. So let's now turn to Ampere's law and do a few problems with Ampere's law. We need cylindrical symmetry with very few exceptions. I have a hollow cylinder here, radius r1.
So again, he's talking like, okay, this is supposed to be about concepts, but what is it about? It's about math. So again, where's the conceptual insights?
Concentric. Another cylinder with radius r2. These are very long cylinders. And assume that there is a current flowing I in this direction on the surface of the inner cylinder, and a current I is returning on the surface of the outer cylinders, and the two currents are the same in magnitude. And I want to know what is the magnetic field everywhere in space. I will make a drawing whereby we only see the cross section. So this is R1, and this is R2. And let's first calculate the magnetic field for R being larger than R2. It's immediately obvious that your closed loop that you choose itself is going to be a circle. That is a must. Radius R. You use the symmetry argument. Whatever the magnetic field is at that distance R, little r, it must be the same everywhere. It cannot be any different here in terms of magnitude than there because of the symmetry of the problem. We have cylindrical symmetry. We also know that if there is any magnetic field that is going to be tangential, either in this direction or in that direction. And so we go around, we make the closed loop integral, use the equation that we have there at the bottom.
So it's not really going around, it's just going to be positive and negative in terms of the little magnets are going to be around the surface, and one side's going to be pointing north and one side's going to be pointing south. No matter where you look at the circle, there's always one pointing north and one pointing south. That's your direction.
And so you get B times 2 pi little r equals mu 0. And now I have to attach an open surface to this loop. I will use the surface in the blackboard. I could use any surface, but I might as well use a flat surface. And now I have to know what is the current going through that surface. Right here, on this surface, the current is going into the blackboard. And right here, on this.
Again, the surface isn't really relevant. The only thing that's really relevant is the surface is used as it being proportional to the circumference of the wire. So the little piece that's you're collecting the field with is the only thing that really matters.
Surface, the current is coming out of the blackboard, the two magnitudes are the same, so the net current is 0, and so the magnetic field outside the second cylinder is 0. So let's now look at the...
Probably not absolute 0, but whatever.
Area in between the two cylinders. These are hollow cylinders. Now this is completely open here, and this is completely open. They are thin material, thin shells are both cylinders. Now, of course, the closed loop is going to be one inside the opening between the two cylinders. And again, I pick radius r. And here I go. I get V times 2 pi r equals mu 0. But now there is current going through this surface. And the current that is going through is I. Not this one, but this one. And so we get I. And so now we get that V is mu 0 times I divided by 2 pi r. 1 over r field. The direction you will find from the right-hand corkscrew rule. That's the way I normally do it. You take a corkscrew and you turn it clockwise, goes into the blackboard, so the magnetic field here is in this direction. If you're not used to turning corkscrews, in corks, think about when you try.
Obviously, the rule applies to external surfaces, okay? So the circle has little magnets going around it. It doesn't have them on the inside, only has them on the outside. So obviously the outside ring, okay, although it is creating a field, isn't creating one with the same mechanism. So it's the outsides that are doing this.
To tighten a screw with a screwdriver, if you go clockwise, the screw goes in. At least that is the case with 99.99% of all screws that you find in this country. They have a right-handed thread. You could make one that has a left-handed thread, but that's not done in general. So now we can go to the area R less than R1. So that's inside this thin shell cylinder. And again, you would take a surface, a closed loop. That is a circle with radius little r. And this is your surface attached, open surface attached to that closed loop. And you will find, for the same reason that you found here, that B is 0 because there is no current going through that surface. And so if you now make a plot of the magnetic field B as a function of r, Here's R1. Here is R2. Then it is 0 here. It's 0 there. It has some value here, which is this value. If you substitute for little r1, and right here, it is this value if you substitute for little r2. And this is a curve that is proportional to 1 over r. And so this is the magnetic field, and inside...
what to say? Again, so it's the surface that's charged, you know, and so it's you have to radiate it out. You can't radiate it in with a solid conductor. So as soon as you bend a solid conductor, you're automatically creating a Venn diagram of sorts. You know, you can have charge on the outside, but you're not going to have charge on the inside.
Seen from where you're sitting, it is clockwise. There is one case, and we did that in lectures, whereby we wanted to calculate the magnetic field inside a solenoid, where Ampere's law works very well.
So inside a solenoid is very different than inside solid conductor tube. So a solid conducting tube, current runs this way, and it creates a magnetic field by making the magnets line up this way. So the magnetism, the current goes through this way, and the magnets line up this way. So you can sort of understand why that would be, and then they're alternating. So that's the other part you got to understand. It's north, south, north, south, north, south, and the positions keeps changing. And the same thing is partially happens with the conducting wire, except everything's happening on the inside now, because now it's the inside where everything gets reflected. But the tubes don't have the same issue with the field being inside the tube. It's running through the tube as a current.
Even though we don't have them closed loops which are circles, we chose a rectangle. I want you to revisit that. It's undoubtedly in your book, and I covered it during my lectures. We assumed that the magnetic field was uniform inside the solenoid and 0 outside the solenoid, which was not a bad assumption. And that allows you then, with Ampere's law, even though you go rectangular, not circular, get the magnetic field.
Right. So there's more than one assumption, right? So the first assumption is we're going to just pretend there's nothing on the outside, which we know isn't true. And then second, we're going to assume that your wire loops, the D and the N number, the number of loops and the distance, make sure that you don't have air gaps in the solenoid. So the wire's as thick as required to fill the gaps.
Inside a solenoid. Very classic. Check your lecture notes or watch my lecture again, which you can do on the web. So now I want to turn to Lorentz force. The Lorentz force, F, is Q times E plus V cross B. This is the charge, which is moving with velocity V in a magnetic field B, and at the location of that charge there happens to be also an electric field E.
Right, so this isn't a real thing at all. So it's true that when you're pushing current, you're going to keep changing these magnetic potentials, so they're creating a moving magnetic field, whether you like it or not, and to a conductor. But the force is not. It's not like I said. I showed the example in one of the other videos where he's saying that Lorentz force is in these directions, when the truth is that's what it's always going to do. It's going to create a force in two directions, but the real truth is those are going to turn into this one direction, and that's really the direction of the force. The force never went this way and that way. The force is definitely going this way, and so this whole Lorentz force thing I think is again wrong way to get the right answer. It creates the right answer in the sense that it always creates symmetry, and through that symmetry it creates the right direction, but it could have got the right direction in the first place and not bothered with the wrong assumptions.
Let's take a situation that I have an electron. Put a minus sign there to remind you that the charge is negative. And let this be the velocity. of that electron, and let the magnetic field be uniform, perpendicular to the blackboard in this direction, going into the blackboard. There is no electric field, so we only deal with Q times V cross B.
Let's just point out again, the electric field and a magnetic field are the same fields. So there's no two different fields. The magnetic and the electric, it's the same energy, same force.
V cross B, you should be able to do that cross product, is in this direction, that since the charge is negative, the force on this charge is in this direction. And so the electron is going to turn over in this direction. I'm going to get a circle if the magnetic field is uniform. And the force right at the center of that circle.
So again, the obvious thing is that there's a repulsive force between B and E. And obviously there's going to be a symmetry to the resistance coming towards it. It's saying I don't want it, I don't want it, I don't want it, and then leaving. It's I don't want it, I don't want it, I don't want it. So it's going to be symmetrical in terms of the going in and the going away are going to be very much the same thing happening. The force will be very strong at one point and very weak, 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 and then weak and strong, strong, strong. You know, so it's going to be exactly proportional. And this is like a perfect illustration of why this just doesn't have anything to do with it. I mean, you could have figured out from the beginning that the end result is the electron is going to avoid, and it's going to avoid in that pink direction.
A little later in time, when the electron is here, going with the same speed, the force is like so. The speed cannot change. The force cannot do any work.
All right, so he wanted those two lines to probably be more even. So they were perfectly pointing the same angle, and the end result of that is that the particle wishes to evade, and it will, if you add up all those little vectors, you'll just get the bottom line, which is it's going to go in some other direction away from B.
And not change the kinetic energy because F is always perpendicular to the plane through V and B, because it's a cross product. And since the force is always perpendicular to the velocity, you cannot change the kinetic energy because you're never doing any work. The only thing that the force is doing is...
And again, there's this assumption in here that this B field is around the whole thing. So you know, he doesn't draw it that way, like you have a continuous B force all the way in this, you know, to create this circle. Because obviously what the particle would do is, yes, it would start off like this, and then when it's doing this V down thing, it would just keep going that way. It wouldn't stay in any circle.
Make it go around. It changes the direction of the velocity. It doesn't change the magnitude of the velocity. It doesn't change the speed. All right? So, let this radius be little r. Combining 802 with 801, we now have that mv squared over r, m being the mass of the...
So that just means he's going to compare this sort of to gravity. So 801 is more about gravity and such, although it isn't, but there's more gravity in it. And so he's just comparing it to gravity. And so what he's done is, you know, gravity is supposed to be this pulling force. He's actually put the pushing force, and he hasn't drawn it as a pushing force. He's just said, here, I have a B field. And like I said, this might be something maybe explained in some lecture we don't get to see, where he points out how, oh, when I say B, I mean B all the way around.
Electron is that force, and since V is perpendicular to B, the sine of the angle between them is 1, and so I simply get here Q, V, B. This is the magnitude of the force, we already know the direction. And so 1 V goes, and so I get that the radius of that circle is mv divided by qb. This being the momentum.
Right, and it's this radius of that circle. There wouldn't be any circle unless the field is continuous. So again, it's just, you know, I think it's just a horrible way of drawing it or emphasizing it or showing it. So I guess when he puts the circle around the B, he's saying it's a circular field. I guess that's the hidden the hieroglyphics
of the electron. So V is the velocity of the electron, speed, Q is the charge, B is the magnetic field, M is the mass of the electron. And as long as this velocity is reasonably smaller than the speed of light, we don't have to make a relativistic correction here. If it's not much smaller than this,
Then they have to add their stupid little gamma, which doesn't add up to much anyway, which is just basically putting a speed limit on where you do the v plus whatever times v minus whatever.
speed of light, we have to make a relativistic correction. I discussed the relativistic correction in my lectures, but I also mentioned that that would not be part of exams, so I will not further elaborate on that. So we will just assume that this is completely non-relativistic. The time for this electron to go around, capital T, is 2 pi r divided by v, but I know r, so I get 2 pi times mv divided by qb. And then I have this v, and I lose this v. And that is not so intuitive, but you see that the time is independent of the velocity of the electron.
So again, I don't even know why this is emphasized, because this is really only has much relevance to accelerators or something. There's no common part of physics where you need to worry about a magnetic field that's circular around something and all that. There's not too many of those in nature.
Assuming that it's non-relativistic. And we discussed that in the framework of cyclotrons. The time for these particles to go around is independent of the velocity. Suppose I have a magnetic field B, which is 7.8 times 10 to the minus 4 Tesla. Now I know what you're thinking. You're thinking, why the hell do you take this crazy value? There's a reason for that, because I have a demonstration here, and the magnetic field is 7.8 times 10 to the minus 4 Tesla.
So it must be an electron experiment, I would guess.
If that is the field, I can calculate how long it takes to go around, because I know the mass of the electron, I know the charge of the electron, I know the magnetic field. So in that case, T is about 46 nanoseconds. And so the number of times that it goes around, F, which is the frequency in hertz, is 1 over the period, is about 22 megahertz. So it goes around this electron 22 million times per second. The demonstration that I will show you, we have a glass container, spherical, it's about yay big, you can see it there. There's low pressure gas in there, so that some of the electrons can go around in a circle before they ionize the gas. We will accelerate the electrons over a potential difference, which I can vary from 0 to 300 volts. And so I can give them a certain velocity. Suppose I give them a potential difference of 100 volts, then Q times delta V, which is the potential difference, would then be 1/2 mv squared. And so if I make this 100 volts, I can calculate what V is, and I found that the velocity of the electrons then is about 5.9 times 10 to the 6 meters per second. So that's the velocity if I have a potential difference of 100 volts. And so I can use that velocity, substitute that in this equation, and then I get the radius of these electrons in that magnetic field, and that radius turns out then to be about 4.3 centimeters. How can I create a uniform magnetic field of that magnitude? It's indeed perpendicular to the orbit of the electrons. We do that using Helmholtz coils. We never discussed that in detail during our lectures. You see here coils, and you see here coils. And when you have two sets of coils like that, and you have a proper distance between them, you can create between them a magnetic field which is almost constant. In this case, this is the field, 15 times larger than the Earth magnetic field. Perhaps some of you remember that I linked you on the 802 website.
I don't know how exactly that would create a, whatever you want to call it, a continuous field, but we'll take a look when we see the experiment, I guess.
2 weeks ago to a very nice program that I received from Professor Belcher, which allowed you
Could be a
to
new
calculate
post.
magnetic field configurations with current loops. And one of the things I
Research.
asked you on the website is try to create what we call a magnetic bottle. This is a magnetic bottle, it's also referred to as Helmholtz coils, whereby you can create between two coils a near uniform magnetic field.
All right, so nearly uniform in this direction, which doesn't sound quite right, but we'll let that slide because I think it's only going to be uniform in one plane. So, one. It's not going to be uniform spherically. It's only going to be uniform in one plane.
And so that's what we have here. And I'm going to show you now how beautiful these electrons go around in circles. They ionize the gas inside, and then through de-excitation of the ionization, you will see light. Just the same idea that you see from aurora. So in that sense, you're seeing an artificial aurora inside a glass tube. I have to make it very dark for this, because the light is not very bright.
Corona discharge. Yeah. Aurora, corona discharge. There's different words for similar things. So what do I want to say about that? Clearly, when electrons accelerate and decelerate, they can potentially, well, not when being accelerated, when being decelerated, they will produce light.
So we have to turn this off. And I have to turn all this off. And I have to turn this off. And some of you who are close can actually see the light immediately in the sphere, right here in front of me. But if not, then you will see it there on the screen. So this is the, let me make sure that I can have my, so this is the electron gun here. It's a potential difference, which I set roughly at 100 volts. And here you see these electrons going around, and they go around roughly 22 million times per second.
It's unfortunate that we don't get to see exactly how the gun is set up and where the electrons are being shot up sideways, which way they initiate into the field. That would be interesting, but.
And the gas pressure is low, so that some of them make it all the way before they ionize the gas. And I can change the delta V. I now make the speed.
So he's saying ionize the gas, but the truth is the electrons themselves are getting decelerated, which is an issue. So they're hitting stuff and hitting it, and they're exchanging energy when they do that, and the electrons themselves might be producing some of the light.
Lower by making the potential difference over which I accelerate the electrons by making that lower. The radius is proportional to the square root of that potential difference. And so now you see here, when I increase the potential difference, the radius goes up. You see how beautiful that circle is? It's absolutely amazing. Very, very nice demonstration.
So what's happening is the two fields are creating exactly the opposite field. I mean, symmetrical. And so at every location, the one thing is further away from the other field. That kind of, it's you're further away from this one than you are from this one. So the two of them combined create inside a symmetrical push-pull.
And then we reach the edge of the, we're now very close to the diameter of the glass sphere, so we can't go much further.
Well, it'd be interesting to try. So there's the gun. The electrons must be produced this way, I imagine. I don't know. Can't really tell from looking at it. It's kind of a complex bit of stuff. There's stuff in the middle there. I don't know what that does. But yeah, I don't know. I don't know what direction they're initiated in. It's more complex than a regular electron gun so obviously there might be some catch to it in terms of how they're initiated, and they might, to get them caught in the field.
So now I want to discuss with you Faraday's law. Faraday's law comes in many different ways. Faraday's law, I will get the Maxwell's equations up again. Faraday's law tells you that the induced EMF is minus d phi dt. D phi dt is the magnetic flux change through an open surface attached to a loop. The loop could be somewhere in your brain, or it could be a real loop. You can imagine any loop in space. That is always correct, that statement. So the EMF induced equals minus d phi dt minus ddt.
So the d phi dt thing, that's the flux of the magnetic field
Of the integral of b dot dA, open surface. You can think of many ways of changing the magnetic flux. One way is a stationary loop and having a changing magnetic field. Another way is of having B constant, but changing the geometry so that the magnetic flux is changing through the surface. You rotate it around or you move things around. Let's look at both today.
Let's maybe save this for next time. Right? We're halfway through or so, so we'll save it for the next time. And such, so forth and whatnot. Yeah. No, I think that's enough. So till the next time.